Exploratory data analysis is a critical component and an extensive part of any machine learning project. It helps us to identify patterns in the data set and gain insights into the relationships between different variables. Overall, it helps us to understand the data better. Therefore, we will now look into a series of code lines that encompass univariate and bivariate analysis techniques under exploratory data analysis. These steps will allow us to scrutinize our data, identify patterns, and extract valuable insights from them. So let us start with univariate analysis. As the name suggests, it is a statistical technique that focuses solely on one column at a time in the dataset. So under univariate analysis, we will look at each column one by one and we will try to find out if there is any hidden pattern lying around in the data. So let us start. Under univariate analysis, we will first discuss the statistical summary of each column. So for that, you can see here in this line of code that we are applying the describe function to the data set. This function is a powerful function that provides a statistical summary of the data set's numerical columns by default. So you can see here in the output that only the numerical columns are present. This function is like having a cheat sheet that offers a quick snapshot of central tendencies, dispersions, and more. So let us break it down. Here we can see that the count is being represented in the first row, which is nothing but the number of non-missing values in each column. This represents the same kind of data that we saw in the info function here. The non-null count is also given in here as well, and we saw that there is one missing value in sepal width centimeter column, and the same is reflected here as well. So this is also one way to identify if there is any missing value in the data set by comparing all these counts for different columns. After that, we see the mean. This is nothing but the average value of each column, following which there is the standard deviation of each column. This represents the measure of dispersion or variability in each column. So you can say that in general that the sepal length of the flowers vary by a value of 0.8. Okay, and similarly in the mean also that the sepal length, the mean of the sepal length is 5.8 and the mean of the sepal width is 3 and the petal length is 3.7. You should note that this is column specific and that the categories are not being accounted for in here. So for this one particular column, that is sepal length, we take the average of all the values that are present in this particular column irrespective of the species to which they belong to. So here the overall mean is there. After this, we see the minimum value. So we can say that in the sepal length, the minimum value is 4.3 and petal length it is 1 centimeter. Okay, so we can say that the smallest petal of the flowers in the data set is 1 centimeter long. After that, we see the 25th percentile or the Q1 value. This value represents the value below which the 25% of the data falls. After that, we see the median, which is represented here as the 50th percentile. This represents the middle value of each column. Following which, we also have the 75th percentile or the Q3 value. This represents the values below which 75% of the data falls. And after that, we see that there is the maximum. So the maximum is the exact opposite of the minimum column. This column here represents the maximum value that particular column is having. So here we can say that in this data set, the flower with the biggest petal length is 6.9 centimeter long. So all these statistical measures here are for the numerical columns, but we can see some statistical measures for the categorical columns as well. For that, we have to make some slight modifications to the describe function. As you can see here in this example, we are passing in a parameter called exclude and setting it with the values of integer 64 and float 64, which is encompassed in a list. So by passing in this parameter, we are informing the describe function to exclude the columns which are having the data types as integer and float. And we see here that all the columns here that are of the type integer and float are these numerical columns. So they are excluded and we only see statistical summary for the categorical columns. There is one more way to get this done, that is by using the include parameter. It is the exact opposite of the exclude parameter. And here we are suggesting the describe function to only include the object data type columns. So if you run this line of code, you will see that you will get the same result, that is a statistical summary of the categorical columns. Also, please note that there are a fewer statistical measures here, only the count, the unique values of the categories that are present in the column, the most frequent category and its frequency. In case all the categories are equal, then randomly the first one is selected, and in this case it is Iris Certosa, because in this dataset all the three categories are having the same count, that is 50. So this was the describe function that we can use to get a statistical summary of the various columns in the data frame in a tabular format. Now we saw that there is one missing value in the data set in here and also at the time of using the info function. So we will have to deal with it. That's because it is always good to ensure that your data is complete before proceeding with more serious analysis. Speaking of which, there is one more way in which we can identify the missing value. We have already seen that we can identify the missing values from the info function and through the describe function as well. But there are some specific functions in the pandas library that are made for this purpose only. One of which is the isNull function. So this isNull function is used to identify missing or null values in the data frame. And it returns a boolean mask where each element is true if the corresponding value is missing. So if a value is missing, then it will return as true, and if a value is not missing, then it will return as false. And once we get this kind of mask, to that we are applying the sum function. So what this function is going to do is, it is going to sum over all the true values in the result of the isNull function. So the isNull function is used to identify missing or null values in the data frame, and its output is generally in the boolean form. So if any cell in the data frame is having any missing value, then the isNull function will return a true value, otherwise it will return a false value. So in this case, when we are applying this function here to the Iris data frame, then what it does is, it will check all the columns for missing values, and if there is even one missing value present in the column, then it will return as true. And then we are just taking the sum over all these values, that is, it will return the sum of all the true values that are identified by the isNull function. So in the output you can see that there is a column-wise analysis of the missing values, and we see that there is one column, that is the sepal width centimeter column, that is having one missing value present in it, and that we can verify from here as well, that it is only short of one value to be 150. So the result, we can say that it is correct here. So we will somehow have to replace that missing value with some other value. But what other value can it be? In this particular case, we will fill that missing value with the mean of that column. So here you can see that sepal width centimeter column's average value is 3.05. Okay, so we will be imputing the missing value with the mean of that particular column to represent an average value of that particular column. So this is the code for that. Here we are making use of the fill NA function. and this function is used to fill missing or null values in the data frame. So whatever value you are going to pass inside this function, it will replace the missing value in the data frame with that particular value. So whatever value you pass into this particular function, it will replace the missing value in the data frame with this particular value. And here you can see that we first access the sepal with centimeter column, and then to that we are applying the mean function. And let's just check whether it is returning the correct value. So you can see that 3.05, that is the same as shown in here. We just wanted to verify it, and this value will be replacing the missing value in the data frame. Now here we have applied the fill function to the entire data frame. So here in this case, because there was only one missing value in the entire data frame that belonged to the sepal with centimeter column, we are applying the fill function to the entire data self itself, because there is only one missing value. But if there were missing values present in other columns as well, and we just wanted to fill in the missing value of the sepal with centimeter column only, then we would have accessed the data frame like this. So by doing this, we will ensure that the fill function is only going to work on this particular column only. But in this case, it will suffice if we apply it to the entire data frame, because there is only one missing value. When you run this line of code, it will replace the missing value in the sepal with centimeter column with the mean of that column. So that is how we can get rid of the missing value from the data set. Also, if you don't want to impute the missing value with any other value, then you can just simply drop entire row itself as well. Let's just take an example here. So let's say if this value was a missing value. Okay, right now it is 3, but just assume that it was a missing value, then it would have been represented as NA or a blank. And this is the only missing value in the entire data frame. Then there is another way that you can deal with it, that is by removing this entire row that contains this one missing value from the data set. So instead of 150 non-null count, all these value would be equal to 149, and that way also there would be no missing value. And for that you can make use of the drop NA function here, which we are not doing in this particular project, but this is also one option to get rid of the missing values in the data frame. This drop NA function is used to remove rows and columns with missing values in the data frame. So now that we have imputed the missing value in the data frame, we can check its data structure again. And now we can see that there are no missing values in the data frame. So that is how we can handle missing values. We can either choose to impute, or we can either choose to drop the entire row or columns as per requirement by making use of the drop NA function. But a few things needs to be considered in case of using the drop NA function to remove the rows and columns in the data frame. That is, if the missing values are less than 10% of the data frame, then you can make use of the drop NA function to remove the rows. But that should not be the case for the columns. For example, if in any one column only 10% of the values are missing, then you should not drop the entire column because of that. In the case of columns, if the missing values are around 70 to 60%, then only you should decide to drop the entire column. Otherwise, imputation is the best bet. You can impute the missing values with either the mean, mode or the median, or the maximum value or the minimum value or any other value. You can also impute the value with the 0 as and when required. So that is how we can handle the missing values. This is a part of data pre-processing, and we are covering it under the data analysis as and when we identify the things that needs to be done along with the exploration. So here we see that now in the data set there are no missing values. So let us now look at the columns one by one visually. So we will first start with the sepal length column that represents the sepal length of the iris flowers in the data set. Here let's just look at the code for a bit. Here we are setting the size of the figure to be having a width of 8 inches and height of 4 inches. And here we are setting the style for the plots, which in this case is white. That is, we are setting a white background without any grids. Then we are making use of the Seaborn library's box plot function to create the box plots, to which the data has been passed as the data frame that we are dealing with, and the x-axis will represent the species of the flower. So we have mentioned the species column as the x-axis, and the y-axis represents the sepal length in centimeters, and here we are setting the palette for each of the box plots here. And then here we are just naming the x and y axis and giving a title to the plot. So this is the resultant plot. You can see that the line in between in these box plots represents the average value, and the average value for iris setosa is around 5, and for iris versicolor it is somewhere closer to 6, and for iris virginica it is around 6.5. So just by looking at this graph, you can know which species of the iris flower is having the longest sepal length. Just by looking at this graph, you can compare the sepal lengths of the 3 different species of the iris flower in this data set. And we find that iris setosa species of the iris flower is having the smallest sepal length, while iris virginica is having the longest sepal length in the data set. So this is one characteristic of the flower that we were able to identify from the data, that in general iris virginica is having a longer sepal as compared to iris setosa and iris versicolor. Okay, so that is how we can gain insights by these kind of visualizations. Basically this box plot here is representing this tabular data visually. Okay, so it represents this 25th percentile, 50th percentile and 75th percentile along with some outliers. We can see that there seems to be one outlier in the iris virginica species of the data. To dive a little bit deeper into this analysis, we can make use of the density plot here as well. This shows us how the sepal length is distributed among different species. Here also, let us just look at the code first. We have just set the size of the figure to be the same as the previous one, and everything is same. It's just that this line here is different, where we are making use of the KDE plot function of the Seaborn library. This function allows us to plot density curves like these that you can see here. So here we see density curves for the different species of iris flowers, and we see the range of their values. So this figure represents the distribution of the sepal length among different species. You can see their density curves being represented by different colors. Blue represents iris setosa, green represents iris versicolor, and red represents iris virginica. In the plot here we can see that there are some regions of overlapping. You can see that some part of iris setosa is overlapping with iris versicolor and iris virginica, and a lot of part of iris versicolor is overlapping with the iris virginica flower. So we can say that the sepal length of iris versicolor and iris virginica are almost identical. That is, there is a very small difference between these two. So it can lead to confusion. Okay, confusion in the sense that all the points that will fall between the overlapping region will be very difficult to distinguish whether they belong to the iris versicolor or the iris virginica category based on the sepal length. And we can say the same about this region as well, where all the three are overlapping. that it will be difficult if any point falls in this value to determine whether it will be present in iris setosa or iris versicolor or iris virginica for that matter, based on the sepal length alone. So these kind of overlapping regions should not be present in the data ideally, because these regions are a reason of concern, because they can confuse our models at the time of making decisions. So a robust model would be the one which will be able to distinguish between these three categories, even if a data point falls between this overlapping region. So let us move forward with the other column, that is sepal width. Then again we see that the width in this case is the highest for the iris setosa, but the length was not. Okay, so we can say that the iris setosa flowers sepals are small and white. Okay, so this is the trend for the sepal width value being shown by the box plot, that the average value for iris setosa is somewhere around 3.5, and for iris versicolor it is somewhere around 2.7 or 2.8. Again, we have a density plot here to show their distribution, and again we see that iris versicolor and virginica are almost identical in their values, that they are having the most overlapping values. So we can say that it will be very difficult for any model to distinguish between versicolor and virginica based on their sepal data. Okay, and it's not only that it will be difficult to distinguish between versicolor and virginica, but also with some data points that are belonging to the iris setosa category, because eventually our aim is to cluster these into different groups, right, based on their similarities. So this can be a reason of concern. Okay, then again here the petal length is there. Now here we can see that iris virginica species is having the longest petal length, that is, and its average value is somewhere around 5.7 or 5.8 we can say, and the trend is similar as to that of the sepal length. So we can say that the sepal length and petal length are the longest for the iris virginica flowers, and they are the lowest for the iris setosa flower. Here you can see the density plot. Now here we can clearly distinguish iris setosa apart from the iris versicolor and iris virginica. You see that there is no overlapping between the values of iris setosa in the case of petal length. So petal length is one feature that will help us to identify more clearly between the iris setosa and the other two species of the flowers. So petal length is that feature which will help us to identify more clearly between iris setosa and the other two species. So at least based on petal length we can say that we will be 100% sure whether a particular flower is iris setosa or not. But we cannot say the same for iris versicolor and virginica in this case also, because we see that there is some overlapping in this case as well, and all the values that will be falling between this overlapping region will pose some confusion to the model. But in this case we can say on an average that a petal length of more than 2.5 centimeter and less than 3.5 centimeter will be considered as the iris versicolor, and a petal length of more than 6 centimeter will be considered as iris virginica. But the values that would fall between 4 and 5.5 would lead to confusion, as it will get difficult to identify whether it is iris versicolor or virginica based on the petal length. And not only the petal length, we saw that the sepal length and sepal width also shows this kind of confusion. Okay, so far we could say that petal length is somewhat better at distinguishing between these three species. Let us come to the next column, that is the petal width. Now in this case we see some different trend from the sepal width. Here the Iris virginica flower again is having the widest petal width. So we can say that Iris virginica flowers are having the longest and widest petals. So we can say that in this data set, all those flowers which are having the longest and widest petal and the longest sepal belongs to the Iris virginica category. And similarly for the rest also we can draw conclusions like these. Now let us look at their density plot. Again we see the same kind of distribution, that is Iris setosa is clearly distinguishable. Okay, the petal width ranging from 0 to 0.5 belongs to the Iris setosa category, and the values between 0.7 to 1 can be considered Iris versicolor, and the petal length that are more than 2 are considered as Iris virginica. But then again also in this case we see some overlapping, and the regions between we can say 1.3 approximately 1.3 or 1.2 centimeter and 2 centimeter can be confusing and would pose some difficulty in identifying whether they belong to the Iris versicolor or Iris virginica. So next we come to the frequency distribution. We want to visualize the frequency distribution, and for that we could make use of different types of graphs like bar graphs, but in this case we are going to make use of a pie chart. Okay, but before we go into that, let us look at this line of code where we are calculating the frequency by making use of the group by function. So here you can see that to the Iris data frame we are applying the group by function, and to this function we are passing in the name of the column by which we want to group the data and get the aggregate values. And instead of getting any aggregate values, actually we are just calculating the size of all the groups that are being formed after grouping the data by the species column. So we know that there are 3 species in the data set, and those are Iris setosa, versicolor and virginica. So we are grouping the data set by these species and calculating their size, which comes out to be 50 each. So all in all we can say that our data set is having 150 rows in it, and that we have already verified in the previous steps. So the count seems to be correct. So there is no imbalance in the data set and all the categories are having equal count, that is 50. So to represent it visually, here we are making use of a pie chart. Here also we are again setting the size of the figure and setting the title as well, and the only line that changes is this line here where we are making use of the matplotlib library to make the pie chart. You can see that the data that we have provided here is the value counts. Okay, let's just see it. The value counts is nothing but the same thing that the group by function here is doing. There is more than one way in which the same thing can be done. Okay, so here also you can see that this is a frequency distribution of the data set, and here the labels are also being given. By the means of label we mean the name of the categories. Let's just print that out for your ease. Okay, wait. So this is a list of the categories in the data set, and the colors are these colors that we have specified above here. So you can see the blue color is representing the Iris setosa, the green color represents the Iris versicolor, and the red represents the Iris virginica. You can see that we have been using the same schemes throughout the graphs to bring in some uniformity in the visualization. So now we are done with our univariate analysis. We have looked into all the columns one by one. Now we move on to the bivariate analysis. So this is also, as the name suggests, is a statistical technique that refers to the analysis of two variables simultaneously to determine any relationship between them. Okay, so instead of looking at the columns one by one, we will look at two columns at one time. So let us start. Here you can see that we have started with sepal length versus sepal width. So we want to analyze whether there is some relationship between these two, and for that we are making use of the scatter plot function. The scatter plot function is used to make a scatter plot like this, as you can see here. Here also all the things are same as we did above, only a few changes are there. That is, the first one is we are using the scatter plot function itself, that is from the Seaborn library, and then here we are using this line of code to move our legend outside of the graph as shown here. So this is the only change in the code. So let us come to this graph, that the x-axis is being represented by the sepal length and the y-axis is being represented by the sepal width. And we have also colored the data points based on their categories, that is based on their species, and iris setosa is being represented by blue, iris versicolor is being represented by orange, and iris virginica is being represented by green here. Here also you can see that from 5.5 to around 7 there is a mixture of iris versicolor and iris virginica. That is, there is no clear separation between these values, right? It represents the overlapping regions in these density plots that we saw earlier. And here the iris setosa seems to be standing out, that is, there are no points from iris versicolor and iris virginica that falls into this cluster here. Okay, so we can see that this iris setosa is standing out as a different cluster, but there is no separation between the iris versicolor and iris virginica based on the sepal length and sepal width in this case, in this particular graph. So let's move to the petal length versus petal width centimeter. Okay, so here there is a different story going on. Now we can see that iris setosa is completely different. It is completely standing out here in this case, in the case of petals. Although it was standing out as separate in sepal length and sepal width as well, but the separation was not by much. But here it is very clear. And also we can see that there is some kind of boundary that we can assume that is coming out to be in this graph between iris versicolor and iris virginica. So there is no intermixing of the values as in the case of sepal length here. So you can see sepal length and sepal width. There are some values here that are like intermixing here, and there is no clear distinction between the values falling in iris versicolor and iris virginica. Okay, so it is coming out to be very randomish here. Everything seems to be random, but in here there is some kind of uniformity. We see that iris versicolor is coming out to be as one cluster, a separate thing, and the iris virginica as well. There is some region from around, let's say, 4.5 to 5 centimeter here. That can be a region of ambiguity, but it is way less than this case. So all in all, from our EDA, we can say that the dimensions of the petal would be better at distinguishing between the iris species as compared to the dimensions of the sepals. So all in all, we can say that through our exploratory data analysis, we found out that the dimensions of the petal of iris flowers would be better at distinguishing between the species as compared to the dimensions of the sepal of the iris flowers. So that is why EDA is very important. We would not have been able to understand all this just by looking at the tabular data in the form of data frame. So that is why EDA is very necessary, and we should perform both kind of analysis, that is univariate and bivariate, to get the most out of our data. So now that we have identified the hidden patterns and the insights from the data set, we are now ready to train a model that can cluster our iris flowers into different categories or species.